Hello and welcome to our webinar titled Intelligent Operations, brought to you by TCG Digital. In this webinar, we are going to discuss how to achieve operational excellence and asset reliability through real-world AI and Gen AI examples in process industries. I am Shayan Basu, joining in from Frankfurt, and I have with me my colleague Nimit Arora, who is dialing in from Dubai, UAE. And together we are going to discuss two real-world examples of use cases for intelligent operations. To set some context, the process industry has historically been seen as somewhat a slower adopter of digital transformation compared to other sectors, particularly those like finance, media, and technology. However, this trend is rapidly changing due to a confluence of factors. This includes market volatility, increasing environmental pressures, and the need for enhanced operational efficiency. Digitalization is fundamentally transforming every stage of the value chain, from raw material sourcing to the final delivery of products. And this integration of advanced digital technologies is driving unprecedented levels of efficiency, safety, sustainability, and profitability. Now, to no one's surprise, artificial intelligence is at the driver's seat. AI is no longer looked at as just a buzzword. By leveraging AI, we are unlocking unprecedented efficiencies, enhancing safety, and dramatically reducing environmental impact. It is allowing us to predict equipment failures, optimize operations, and manage complex supply chains with a degree of precision never seen before. In a sense, while digitalization lays the groundwork by digitizing information and processes, AI provides the intelligence to leverage the digital foundation for superior performance, cost savings, safety, innovation, unlocking value that legacy systems alone cannot deliver. In this webinar, we are going to dive deeper through two real-world examples for showing you how we can achieve such operational excellence and asset reliability through applications of cutting-edge AI tools. Let us move into these use cases. So, in the first case study, I'm going to share with you our experience of working with one of the largest petrochemical companies in India in the space of real-time optimization of assets. The client is a large producer of petroleum products like ethylene, propylene, benzene, along with polymer derivatives. So in this case study, we will try to outline how it was possible to achieve a significant boost in margin and yield through implementation of the RTO for one of their cracking units. Now let us look into the business case first. Starting with a bit of a context on why and when a real-time optimizer would be needed. As most of you are aware, the cracking process in petrochemical companies comes with a set of inherent challenges. First of all, there is process nonlinearity and complexity. As cracking reactions are highly nonlinear and temperature sensitive, even small changes in temperature or feed composition can cause large shifts in product yields. Then there is the case for feedstock variability. Most of the plants often process mixed or varying feedstocks due to financial constraints in raw material sourcing. Now, variations in feedstock like naphtha composition, paraffinic, olefinic, aromatic content in naphtha, etc., it can affect yield and coke formation. Then there is furnace operation and severity control. Cracking severity must be carefully controlled, as we all know. Over severity often increases coking and maintenance costs. Under severity will reduce yields. Then there are economic trade-offs in the crackers because you need to accurately balance production of ethylene, propylene products based on market prices. So energy and utility costs vary with load and cracking severity. There are equipment constraints. Furnaces, compressors, quench towers, etc. often have tight operating limits. Now, manual operations can either push limits unsafely or leave value to the table. So this is where an RTO can add enormous value. In a sense, an RTO in a cracker acts as a higher level cognitive control that will guide the lower level control systems in the plant. It moves the cracking limit towards the most economically advantageous operating point, considering all the complex interdependencies and constraints and adapting to the ever-changing conditions. This leads to increased yields of high-value products, reduces energy consumption, and improves overall profitability for the refinery or the petrochemical complex. Now let us dive a little deeper into how an RTO looks like. So in essence, an RTO is made of the following core building blocks. First of all, there is an objective function, and the RTO is programmed with an objective function which will represent the plant's economic goals. This goal could be maximizing profit, which is revenue from products minus cost of feedstock, utilities, catalyst, as you know. It could be maximizing the yield of a specific high value product, for example, propylene, or minimizing energy consumption. The second important aspect of an RTO engine will be the kinetic model. The kinetic model is a proprietary plant model which is developed as a digital replica of the plant or the asset across each point of the process flow, which helps us estimate the plant outputs which will be needed to optimize the objective function. The kinetic model, as we all know, is usually proprietary to the licensor who has the ultimate know-how of the furnace design. Then we have a set of AI algorithms using advanced AI algorithms like nonlinear programming or neural networks. The RTO can search for the optimal operating conditions, which are set points for the controllers that will maximize the objective function while satisfying all the constraints. And finally, we will have the constraints, of course. The optimizer has to incorporate the operational constraints, which are the limits within the plant can safely and effectively operate. These constraints can be of various ranges. There can be equipment limits like maximum temperature, pressure, flow rates, etc. There can be product quality specifications like octane numbers, purity for olefins. There can be environmental regulation conditions like emission limits for carbon dioxides or oxides of nitrogen and sulfur, and so on. In the next slide, we will dive a little deeper on how an RTO actually works. So as you can see on the slide, this schematic describes the implementation topology of an RTO for a naphtha cracker. So at first, the user will set up the problem by entering the acceptable range for each independent variable, the economic data, and the constraint limits. The user will then initiate the program. The data acquisition software after that will gather and validate the historical data from the plant control system so that the process model can be loaded with the current plant information for feed composition, excess air, fuel composition, etc. The data acquisition system will also collect and validate the plant data that corresponds to the current plant values for the independent variables. Now the optimization cycle will begin by loading all the data collected by the data acquisition software and loading all the static data, also as shown in the slide as one-time input data, as you can see. The values of the independent variables are set to the current plant conditions for the first iteration. Now, the kinetic model that you see at the center of the block will simulate the heaters. The values of the independent variables, as well as the resultant combined effluent and heater conditions, will be used to populate the constraint variables. The heater conditions and combined effluent will also be used to evaluate the objective function. The value of the objective function and constraint variables are passed back to the optimizer, and the mathematical optimization algorithm uses this information to generate a new set of independent variables in the direction to maintain feasibility and increase the objective function value. So this process continues in an iterative manner between the kinetic model and the optimizer until the optimization algorithm is satisfied that it has found the best or optimal set of independent variables. These variables will then be passed on to an output dashboard for manual implementation in case of an open loop system, or it can directly be fed into the APC within the plant for a closed loop control. So this is at a very high level how an RTO unit works at a RTO engine works at a naphtha cracking unit. Now let us move to the next slide and look into that what could be the measures of benefits from such an RTO implementation. As we all know, the success of any AI implementation project will depend explicitly upon the value that it generates over time. So to ensure that the implementation is successful, it is crucial to periodically evaluate and measure the incremental value that the project is generating in a quantifiable manner so that the return on investment can be determined effectively. In this particular implementation, we could successfully realize an overall increase in profit margin, better yield, and reduction in energy consumption. As you can see, the slide also depicts some of the quantified cost savings that were observed over time for the plant where the implementation was done. So this brings us to the close of the first case study that we wanted to take you through in the area of optimization of assets. Now we will move on to the next interesting case study that we have, and I will request my colleague to take us through this. Over to you, Nimit.
Okay, thank you so much, Shine. So the next case study we're going to talk about is for a large petrochemical plant. We have been able to use AI to improve reliability and build predictive asset management capability. So we'll walk you through this case study. So what is the challenge when we try to do asset management and in a predictive manner? So when we look at the plants in process industries, they need actionable insights beyond your standard monitoring. So your condition monitoring systems, equipment monitoring systems, they're able to monitor, but you need to be able to generate actionable insights. Additionally, all these systems need to be very, very specific to the plant's conditions. So right now, the generic systems fail to detect specific anomalies within the plant. And once you identify any abnormal behavior, how do you ensure that, okay, somebody needs to take an action on it? So there needs to be a quantification of what could be the severity and the financial impact. And finally, you need to have timely troubleshooting and actionable insights that you need to be able to generate so that somebody can take an action on it. So these are the challenges faced when we try to do asset management, and AI can really help a lot in addressing these challenges. And we'll show you how in the next few slides. So our AI-based asset management solution composed of these 5 components. So to begin with, we need to start monitoring the critical process limbs and other assets. So we need to start monitoring them. And once we monitor, you also need to build a detection engine. So these tags that are coming in into our system, we will be able to look at, okay, what are the different types of anomalies that could be detected using this detection engine. So there's an anomaly detection piece. And once these anomalies are detected, you need to be able to identify, okay, what is causing these anomalies. So what we show in the third box here is we build a knowledge base using your existing assets, existing documents, and generative AI. We are able to create an analysis and knowledge database that can be leveraged. The fourth component is looking at what could be the opportunity or repair costs. So this is where we bring in past historical maintenance data and repair data and tie it with the knowledge base to estimate what could be the potential losses. And finally, you look at once the causes are identified, what are the corrective actions that can be taken? Again, we use generative AI here to come up with corrective actions in simple, plain engineering language that the engineer can understand and take really good actions on the field to prevent this anomaly. So that's the overall schematic. Now we will look into each of these in detail in the next few slides. So as I said, the first step really is to monitor the assets, and especially the critical assets. You already have DCS systems, but this is additional to the DCS systems where you're monitoring key KPIs, key parameters, for example, pressures, conversion, yields, efficiencies of your boilers and compressors. So we bring all that data into one repository. And along with that, we also bring in other data such as failures, downtime, repair costs, lost opportunities. So these are all bring into one place, and you start monitoring these critical assets. And then the detection piece comes in, right? So we look at the tags, and there are 3 components where things can go wrong. So one is the instrument can trip, right? So you have your trip limits in the DCS system, high, 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 low, low, and low. But before you reach the DCS limits, we're building a system where you can actually get alarms to the operators so that you take action before you hit the DCS limits. So we calculate something called a trip score. So it will give you an indication of how close you are to those limits. Similarly, on the right side, we show SRI instruments. So if you have any faulty instruments, which is like frozen values, or they have a sudden deviation between the values from the previous time scale. So it will be able to detect those faults within the instruments. So that's another area. And the third area is detecting anomalies. So this is where we look at different parameters together, how they are correlated, let's say temperature and pressure, vibration sensors. So all that we correlate and see if there is any abnormality in the behavior. And in certain cases, we also model certain process anomalies, for example, CO2 slippage or sulfur slippage. So we build AI models so that we can actually detect these behaviors and set alarms to the operator in a very visual way that they can easily look at and see, okay, there's a prediction to have this kind of anomaly, and then they can go into further actions. The third step is building that knowledge repository. So this is also a key element where we bring in insights from your existing documents that you may have. So you have your SOPs, manuals, other repair records, historical RCAs that you may have done. So we use generative AI to bring all this knowledge uh, together in a very searchable knowledge base. So you can use this as a knowledge base, but in this case, we are using this to augment the asset reliability function. So once the anomaly is detected, the engine will actually go and search this knowledge database based on the contributing factors. You can look at, okay, what could be the most probable cause for these anomalies, and there is also a reference. So the engine will be able to reference the exact documents that were used to generate this insight. So maybe in the past you have seen similar events. So it'll be able to go to that document or the SOP or the operating manual where it will exactly show you, okay, if this anomaly has happened, what needs to be done. So next, in step 4, we are looking at how the anomalies are showed. So this is one example where it's showing an anomaly detected due to PTA water operation. So it's really looking at all the tags, the knowledge base, and then showing the anomaly in a very engineering and human kind of language, right? And then the second piece is once the possible causes are identified, to bring the financial data, the historical records, and look at, okay, has this event happened in the past? And if it has happened, what were the financial losses? What was the repair cost? How long did it take? What was the downtime? So all that information can be seen, and you can even see the history of what was done by the operator and the engineer, how they corrected this problem. So all that history can be viewed. And so that really gives an indication to the operator, okay, how severe this problem could be. So many times we worry about false positives in the world of using AI for asset reliability, but this gives you assurance in terms of uh, is this problem really severe? Do I really need to take an action on this, or is this a very small problem that I can maybe ignore for now? And then finally, the last piece is guiding the operator through what we call decision trees. So once you have identified, okay, this problem is severe, now what do I need to do about it? So the next step is taking action. So we could build process fault trees or equipment fault trees. And again, we can do this using generative AI, using existing documentation, or this could be done using your expertise that you may already have in the plant or experts from outside. So we build this process tree, and then using the data coming in, we can really traverse the process tree and identify, okay, what actions need to be taken. So it has various recommendations that can be provided. And you can see in the next slide an example of what the recommendation could look like. Right. So again, this is shown in a very human language, so it's very easy to understand. and again, bringing in the process knowledge, bringing in the OEM knowledge into the mix, and giving concrete recommended actions, both if you want a temporary solution, there are a set of actions that you can take. For example, here, it could be just changing a simple filter, or changing the trays, or it could be something bigger that you may need a lot of, you may need to take the equipment down for a couple of days, do the repair work, and then bring it back up. So again, based on the severity and the detection, we have that scoring mechanism, right? So based on the score you get, the health index score, we can identify whether it requires a temporary solution or a permanent solution, and it gives you all the steps that are needed to be done. So it's really bringing a mix of both AI and process knowledge together. And this database keeps updating, right? Because we keep getting new data from the plant condition keeps changing, your efficiencies keep changing. So we have this auto tuning feature where the new data will come into the plant, and it will be able to auto tune the models and bring in that new information. So that's covering all the pieces of the asset management work that we've done for this petrochemical plant. So some of the key takeaways from this previous slides are: the AI can predict anomalies in the background. It can analyze how critical the alerts are. It can give you a scoring for different components. And then using Gen AI, we can show what are the potential contributing factors. So going one level deeper, and then you can look at the alert importance. And finally, you can get some insights into what could be the costs and the potential losses to look at the severity and some recommended actions. And so this really gives confidence to the operators. Okay, this AI is not a black box. It has some process, domain, and knowledge that has gone into, combined with the powerful things that AI can bring in, to actually build a more robust solution where it can really help boost the reliability, reduce unplanned shutdowns for the plant, and really bring massive benefits. So that concludes the section on the second use case. So we have showcased you 2 use cases, but there are various other things that can be done using AI and combining the process know-how. So just to give you some example, we have done over the last 5-6 years, we have done a massive transformation for a petrochemical plant and resulted in significant economic benefits. And you can see at various stages in the value chain, starting from procurement to production, maintenance, distribution, AI can play a big role, and some of the use cases are shown here. So these are some examples where we have done RTOs, let's say, planning. On the planning side, we have done sequence optimization, we've done pricing analytics on the supply chain side. So there are a lot of things that can be done, and all this is enabled. So really you need a solid platform, and what we have within TCG Digital is a platform called MQ. So it's an end-to-end AI platform which brings all these components together, starting from ingesting data from any system, historian, or other enterprise systems. It has a very robust data layer, semantic layer, a large library of AI algorithms that we can use, a visualization layer to create dashboards, and then there's also the agentic AI framework that can build these AI agents, which can help you improve your plant production, optimization, reliability. So it can do a lot of things that are needed to accelerate digital transformation in the process industries. So that concludes our presentation today. This is our contact details. If you have any further questions, please feel free to write to us. And I think we'll now open it up for questions. Shayan, do we have any questions?
Thank you, Nimit, for taking us through that examples. We do indeed have some questions coming in. So I think let us quickly take some of these based on whatever time we have left. So The first one is a very standard question, I believe, that we often encounter. The question is, how is an RTO different from an APC in the context of plant operations? Nimit, would you
Okay.
like to? Yeah,
Yeah. I'll take a stab at it, but feel free to jump in. I
sure.
think it's a very common question that we get. So APC definitely has its own role, and it has provided significant benefits to the plant operations. And as you know, all know, APC is a plant control system. So when I think of APC, I think of it as a cruise control in your car. So you set the speed limit that you want the car to go at, and the APC does all this minor changes to maintain that speed, right? And but what speed is optimal for the car, that is decided by RTO. So you can think of RTO as an engine which decides what is the optimal operating conditions for a plant, at what temperature will I get the maximum yield, at what operating set points will I get the maximum profit margin. So what we have seen from our experience that even for the plants which have APC, RTO is able to generate around 3 to 5% additional benefits. And especially for the process industries where the you have very complex chemical processes that's going on. So many times the APC models are not able to capture the full value, and also the plant keeps changing, right? The behavior of the plant. So an RTO is able to keep up with the plant behavior, plus give you the additional 3 to 5% benefit.
Great. Thanks for explaining that, Nimit. I think we have another question which is also related to the RTO topic, and this is a little specific one. It says, how does an RTO react when the plant is not in a stable operating mode?
Okay. Yeah, that's a very good question as well. So what we have done in our solution is, yeah, totally understand RTO typically does not work in dynamic conditions where the plant is in unstable operation. So what we have showcased you is a steady state RTO optimizer. So what we build is a steady state check before the RTO run. So it looks at various parameters. For example, in the ethylene cracker, it looks at how the flow is varying. Is there a significant variation in the feed flow? Is there a significant variation in the coil outlet temperature? Uh, is the heat and mass balance more than 10%? So there are various parameters that we look at, and we identify whether the plant is in steady state or not, right? So we keep doing that, let's say every 5 minutes. And if the plant is not in steady state, we don't run a new optimizer. And but when we keep checking this every 5 minutes, so as soon as the plant comes back in steady state, then we can run the optimizer, and then you can actually, you will get the recommendations, and then you can implement those recommendations. And additionally, the other feature which we have added is typically you don't want very diverge changes in your recommendation. So it should not
Mhm.
happen that your current COT is, let's say, 800, and you suddenly, the RTO says you want to change it to 820. So that the
Right.
sudden step changes are not recommended. So in the RTO, we have built logic so it only changes using smaller step changes that are allowed in the plant.
Right. I think these are finer controls that can be built into the operational constraints layer in the
Absolutely.
overall RTO architecture. Right. Thanks for taking that, Nimit. I think we have time for just one more. So let's quickly go through this. There's a question around the asset reliability solution, which is what kind of data sources will be potentially needed to implement such a solution that was described. I think, Nimit, you briefly covered this in one of your slides, but I think we can provide some further elaboration.
Absolutely. So that's another great question. So there are two parts to it. One is the data itself, right? So in terms of the data, we definitely need all the equipment and sensor flow meter data, which could come from DCS or historian. We need the previous historical maintenance data and the repair data. We will need the SOPs, the operating manuals, RCAs, even as I said, we are bringing in the cost aside, right? So we will need to get either from the ERP system or from your maintenance system. So the more data we have, the better the system will work. And in some cases, you may not have the exact failure or the anomaly happened in your plant. So what you would do in those cases? So that's where you bring in the process expertise and the operator expertise. So that's also very critical. It's not just an AI black box. We bring in that expertise and we build in features, as I said earlier, of reinforced learning and auto tuning. So the AI will learn from plant behavior. So even if, let's say, the event happens in the future after we implement the system, then we will raise the alert and alarm through the other components that we talked about. And then over time, the system will really learn that this anomaly has happened. And then whenever it happens, then the next time, then it will be able to detect and be able to, flag that anomaly and recommend corrective actions.
Right. So I think it is fairly standard like any other AI implementation. So better the quality of the data, the sufficiency of the
Absolutely.
data sources, better is the accuracy of the model. But what we are hearing is even if there are a dearth of data sources, even through reinforcement learnings, over a period of time, we can build in that accuracy into the model and we can help the plant achieve incrementally improving operations. So I think we don't have time for any more questions, but there are quite a few that we would have liked to go over. So what we can do is, in the interest of time, we will close the session, but we will make sure that we respond to you in writing against each of your questions. And if you have any further questions based on the sessions today that we went through, please feel free to write to us in the credentials which Nimit talked about. So that brings us to the close of today's session. We thank you all for your time, for joining, and wish you a very pleasant day. Thank you.
Thank you, everyone.